We saw how we can build a schematic using Xilinx ISC, and we wrote a test bench and tested the same. So in this, let's write or design a circuit using Verilog, and we will test it out. So again, launch ISC. You get to read a new tip every time, that's fine. Let's create a new project, file, new project. And one of my all-time favorite functions is called an AOI22, which stands for AND or invert 22. Now, what is an AOI22? It's easier to pull it up on Google rather than explaining it. Look for AOI22. It's called AND or invert. So an AND or invert is a really neat way of implementing a lot of function using as little transistors as possible. It's not important for you guys, but as a digital designer, this is one of my absolute favorite gates. So this is how it looks. It's an 22 AOI symbol, and it's A and B or C and D the whole bar. So that's what it is. It's A and B or C and D the whole bar. This is an AOI22 function. Cool. So let's say I implement an AOI22. Again, it's going to be of the source schematic. Click on next, and I will not change these. It's the same thing that I chose, same settings I chose the previous time. Next, and now again I want to make sure that I'm on my implementation view, and previously when I added new source I chose schematic. This time I will choose verilog module, and let's give it a name. Let's give it AOI22, and generally I like to name my verilog files with an _v, so that when I look at it I understand that it's a verilog file. I am not going to be changing my path. Hit on next, and now you see a new window. Now my input is going to be A, B, C and D. So these are all of direction inputs. So I have an input, I have an input, I have an input, I have an input, and then my output, which is F, is of the direction output. Now, these are all single bits, so that's why I would not mess with my bus or my MSB and LSB. If, for example, A was a two inputs, then I would click on bus, and my MSB would be 1 and my LSB would be 0. If A was 4 inputs, then I would again click on bus, and this would be 3 and this would be 0. But for now, since it's all 1 bits, it really doesn't matter. I'm just going to deselect my bus, make sure that I have my 4 inputs, A, B, C, D, which are all inputs, and my F, which is an output. Then click next, and this is another summary page which will help me verify if all my settings are right. Looks like it's all good. Finish. Again, how we saw that Xilinx created a normal skeletal code for our test bench, it's going to do the same thing for our verilog module as well. It's automatically created a timescale which it's going to use for reference. It's created a module, and the name of the module is AOI22_v. The inputs are A, B, C, D, and my output is F. Now let's use structural verilog description for this particular project. Now let's take a look at, let's do this, and let's take a look at this. So the symbol is going to be, this is my symbol. So let's scroll down. So first thing I'm going to do is AND A and B and output it to a wire 1. So let me define a wire 1, right? And then I'm going to use AND. I'm going to give an instance name, call it U1, which the output of which is going to be wire 1, and the inputs are A and B. Perfect. Next, I have another AND gate which is connected to C and D, and let me call that output to be wire 2. So let me add wire 2 to this guy. And let's come down here, let's add another AND gate, and let me call it U2, output of which is wire 2, C and D. Now, you can implement this using a NOR gate. This is a NOR gate, or what you can do is use an OR gate and follow it up with an inverter. So let me just use a NOR gate for now. So let's put up a NOR U3. The output is F, and the inputs are wire 1 and wire 2. So this should be good. Let's get back. Looks like my design has A and B, C and D with a NOR. Let's save the design Looks like there are no errors, so this is good. And next, once you have a design, you need to test it out. And you test it with a test bench. Again, right click, new source, verilog test fixture, and let me call this AOI22 test bench. Very simple. I'm not going to change my path. Next, I'm going to choose my top module to be my verilog description. Next, and finish. Again, this is going to create a very similar test bench skeletal code like how we saw for the schematic. You see that it has a timescale generated and a whole bunch of comments, and you see that the module is of type test bench. My inputs are registers, my output is a wire, and it has instantiated my unit under test, and also initialized all my inputs to 0, and it has waited for 100 screen units so that there's a global reset. Now, this is where I add my stimulus. So initial, begin, and now. As a designer, it's really helpful to write your test benches in a really neat, concise, clean way. So because I have 4 inputs, that means that I have 16 test cases. I generally like to exhaustively test all my designs just to be sure that my design works the way I want it to for every single input case. But if you have, let's say, a 100 input gate, then it does not make sense to test for 2 to the power 100 test cases. That's when we start applying a little bit of optimization techniques, and we will not want to test for 2 to the power 100 test cases. We will, in situations like those is when we will want to test a design with less number of test cases. But for this, let me test for all 16 test cases. So one way to do this is physically write A equal to B, 0, C equal to 0, D equal to 0, and then wait for 10 screen units, and then copy this and make it 0001, 0010, all the way till 1111. That's going to take a long time. Another easy way to do this is use for loops. So for loop is very similar to how we write in C program. So you have a for, you have the body inside this, and then you have an opening brace and a closing brace. The opening brace is going to be replaced by begin, the closing is going to be replaced by end. That's it. And now you have your for loop. Now, before this, let me define a temporary variable of type integer, and let me call it temp, which is going to be type 4 bits, 0, 0, 0, 0. Why 4 bits? Because I have 4 inputs, A, B, C, and D. That's it. So let me get rid of this. Now in this, let me make temp equals to 4-bit binary, 1, 2, 3, 4. And I want to run the loop for all the 16 cases, which would then mean that my temp is going to be 1, 1, 1, 1. And for every loop, I want it to increment by 1. So temp equals to temp plus 1. Now, one way of implementing this is A equals to temp. Because it's 4 bits, it's going to be from 0 on to 3. So it's going to be temp of 3. Let's see. This is perfect. B equals to temp of 2. C equals to temp 1, D equals to temp 0. Again, let's give 10 screen units of delay. And I am really not interested in checking if this design works through waveforms. I would prefer to have it printed out. So let me use a .display command. Display is very similar to printf statements in C programming. Let's A, B, C, D equals to %B, 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 and this is my out equals to %B, right? And A, B, C, D, F. Perfect. So this is a much better way of writing a test bench. Now, there is another way of writing this. It's called concatenation, in which instead of doing something like this, if you guys have not learned concatenation in class, it's fine, don't worry about it. So I'll just comment that code. When you concatenate 2 bits, you put it inside these 2 braces, and then so let me concatenate A, B, C, and D, right? And I just give them to temp. So what this does is automatically sets temp 3 to A, it sets temp 2 to B, temp1 to C, and temp0 to D. So this is an even better way to write a test bench. So let me test out a test bench through this, and then I will comment these out. I will uncomment this, and then let me test out using this code. Let's save this for now. Let's jump to simulation. Oh, there are errors. Let's see where it is. Line 57, right here, integer temp, syntax error, initial begin, temp equal to 1, 2, 3, 4. Oh, I am not supposed to put this here. Cut. Paste. So my integer should be there. Line 58, initial begin. Oh, that's right. I already have an initial begin right here. Save. So syntax near end. Oh, that's because I have an extra end. Cool. So now I should not have any errors. That's perfect. So the error was the skeletal code already had an initial and begin, and I put an initial begin inside an initial begin. That's an error. That was first error. And the second error is my integer should always, my temp variables or any integer variables should always be defined before my initial begin. So that was my second error. Looks like now I have no errors. Let's go to simulation. Let's click on this. I want to verify that I have my top module is my test bench, and my unit under test is my verilog description. That's good. So let's click on my test bench. Let's go to isim. Let's check syntax. It passes. So it's time to simulate my behavioral model. So looks like it has its waveform generated. It's much easier to kind of look at it this way. So 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, and all zeros. Let's take a look at the truth table. Let's see. Okay. Zoom in, zoom in, zoom in. Yep. So this is good. So you have 1, 1, 1, 0, 1, 1, 0, 1, 1, 1, and all zeros. That's exactly what we have right here. 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, and all zeros. So now let me close this. Do you want to exit application? Yes. Let's minimize this, and let me comment this out, and let's use the other way of writing test benches by concatenation. Let's save this again. No errors. So let's check syntax. It passes. Let's simulate my behavioral model. Perfect. It's simulated, and I'm getting the correct output. So 1, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, and all zeros. So this works exactly how we expect an AOI 22 gate to work. And the real meat in this video is writing good test benches. So you can spend a lot of time writing really crappy test benches, or you can spend just not more than a minute and write a really efficient test bench, something that tests your code exhaustively. So that's pretty much what this video is all about. Alright, so next video I will talk to you guys about how to generate the UCF files, the .bit files, something that we can use to download our piece of code onto our FPGA kit and test it. For now, see you later.